We'll be talking about, we'll be finishing up with Zonzig's perturbation theory, and I will show you how to derive something that you have all probably seen. If you have taken the prerequisites for this class, which is Chem and thermodynamics, then you have definitely seen it, which is van der Waals equation of state. And this will give you intuition into how this perturbation theory works. And like I mentioned last time, it's way more powerful than what we have seen today. At least one of the three papers uses it in context of drug design. And you should browse through it even if you decide not to survey that paper. And you will see how immensely useful the perturbation theory ideas are. But today we will use it to derive van der Waals equation of state. That won't take too much time, and I think, or at least maybe half the class. And then we will start doing Ising models and phase transitions. So you on my iPad, you probably see my webpage. Yeah, you do. So on this, I have, first of all, these are the three papers for the midterm, and this one, and I have posted the PDF through my Google Drive. You can see this is the Journal of Medicinal Chemistry, which is a legit journal. I don't think I can even publish that because they really don't like simulation papers. They really care for papers which are well grounded in experiments also. And this is a nice review. It talks about many complicated things. You don't have to go through everything. But the key ideas here are the perturbation theory relation. So that's one paper that you can do. The other option is this review. It's an old review, but it's actually a review in Science, which is the most highest impact journal, written by John Weeks and David Chandler. These two names you probably know. Hans Anderson was a professor at Stanford. So the chapter 7 of Chandler is essentially based after this review paper. So in previous years in this class, I would assign only this paper to be read, but this year I thought I would give more options. And the third paper that's on the list is actually a blog post. One moment. I'll remove the waiting room. This is a blog post by a PhD student at, yeah, well, just a moment. I cannot let Kel in. This one is a blog post by a PhD student at Princeton, and it's a wonderful blog post which talks about how certain ideas that you will be seeing in the context of Ising model, which actually started with Feynman's work in 1960s. It's called Gibbs-Bogleubov-Feynman inequality, how they are used in machine learning. So this is a quite a nice blog post. So you have choice of these three to go through, and I recommend, I strongly request, actually not recommend, that you at least browse through all three before making your mind. So any questions about what we have done so far, or anything else? Okay, if no questions, in any case, you can ask me later if you have any questions. Let's start with today's thing. So today, what's the idea in Swan-Zig's perturbation theory? The idea is that if you have a true potential, and what's the symbol that we have been using? The true n-body potential, let's decompose it into a potential coming from a reference system, let's call it UN0, plus a potential coming, the difference. So this is exact. There is reference, and we call this perturbation. Perturbation is a word that means a small difference. So if your reference is very far from the true potential, then the perturbation will be non-trivial, and such an approach might become useless. And the formula that we derive, which I again request you all to try to do it after closing your notebook, and try to do it on your own, thinking through it, and see if you can do it on your own. If not, then it means that there are still certain gaps in your understanding of this material. So it's worth doing it. EXP of minus beta UN1 calculated in the reference potential. So this is a wonderful formula, because what you need to do here is to calculate the partition function of reference potential and calculate average of some quantity in the reference potential, not in the true potential, in the reference potential. And you can see why this is very relevant. So now imagine you're interested in studying some polymer. Okay, so you have some complicated polymer where everything is talking to everything else and it's a whole mess. The polymer is really complicated, but imagine that you could change this into a reference system where the polymer beads can really cross over each other without any complication and the interactions are very weak. So simulating this system on the right would be much easy, or studying this in an experiment. In this one, you will have to let it sit for a very long time for anything to happen. So when I do computer simulations, so I tend to get biased towards computer simulations perhaps a little bit, but all these ideas apply to experiments also. So this is, say, let's say this is a very viscous system. It will take a lot of time to settle to anything, while this one is easy to move, everything can be done. So you can calculate the properties of this viscous system by instead studying the easy system. That is the most important lesson in science and everything else, is that there is never a free lunch. Even though as grad students, you might be led into thinking there are always free lunches, seminars, this and that, but no, there is never a free lunch. So there is never a free lunch. And the problem in this is that if the reference potential is very different from the true potential, the term UN1 can be very different from non-zero. It can be a very small number, a very large number. A small number is not a problem. A large number is a problem, because then if UN1 is a very large number, then e to the power minus beta UN1 becomes 0. And calculating the average of this quantity over here becomes an extremely difficult task, because you are trying to calculate the average of something which is very, very small. So if you try to calculate it, it will just be 10 to the power minus 18, which is computer zero, and will run into problems. So, but let's see how to do it in practice. So today, what we are going to do is to apply this statistical mechanics perturbation theory to derive van der Waals equation of state. So you are all probably familiar with van der Waals equation of state. It starts by saying that P by KT is equal to rho. That's our ideal gas. But then it says, well, it's not just rho. Let's think about rho divided by 1 minus B rho, which B accounts for volume of the particles. And there is a second term minus A rho square by KT. So this is a correction in the van der Waals equation of state, which you have all seen. Today we will see why exactly does it have this form. You should already have some intuition for it. What you are seeing here is that there is a term in the power rho to the power 0, then there is a rho to the power 1, and there is a term rho to the power 2, and there are no higher order terms. So, but let's try to derive this from a very fundamental perspective. So to do this, let's consider our full system, which is U, made up of n particles. Let's assume that it is made up of pairwise additive interactions. So what do we mean by that? We have seen this in the past. So this means that it is I more than j more than equal to 1 going up to capital N, some small u, which is kept same for all pairs ij. And this itself is given by, this itself is a function of the distance between Ri and Rj. So yeah, so one of you asked me that we had not completed the perturbation free energy expansion. I had provided it in the notes, and the only thing I was missing, if you see in the notes, I had gotten till this part, and the part that I was missing is that e to the power W1 minus beta. So you had these two terms. Sorry, I'm just switching gears suddenly, but I just wanted to say that this is the additional part that I added in the notes. This is not hard at all. The only comparison change that I was missing in class that time was to use e to the power x is approximately 1 plus x. Once you do that, you just compare the powers of beta and you get this. And as a do-it-yourself, I want you to derive W2, which is a bit trickier. So I won't say too much into it. There is nothing profound. The only thing that I was missing was e to the power x. One. Thanks for reminding. So, oh wait, where am I? So we have this pair interaction. So today, and what would this pair interaction look like? This pair interaction could look like anything. This pair interaction could look something like this: U versus R, or that typically that's not a common form that is used for a pair interaction. A more common form is something that looks like this, and where this slowly goes to 0. So this is A by R to the power 12 minus B by R to the power 6. This is a more common form. So these are examples of U. But we won't be assuming a specific form. We will be working with a generic pair interaction, and we don't know what the form is. What we will be doing is to decompose this into a reference plus perturbation. Okay, so how do we do that? So we take our small u of r, this is not capital, this is the individual pair that is contributing to everything, and decompose it into reference. A nice reference would be to take ideal gases, then there would be no computation to do. Running the simulation would be very simple, or the experiment, but we don't do that. We take as a reference as a Hart sphere. And often in using these calculations, in reality, it's all about choosing the reference correctly. If you don't choose the reference correctly, it might become useless. So in this case, turns out that Hart spheres are good reference to pick. So we would write it as a Hart sphere plus some perturbation U1 of R. So how would this look like? So let's say that our true U of R is looking like this. So what we have said here, that let's break it into two parts. Let's break it into a reference that's going to look like, what does a Hart sphere potential look like? It's infinity over here, and then it drops to 0. And before any of you get angry over this line, this is just for your visual aid. It goes up to infinity, and then it drops to 0. So if that is our reference potential, then we can see how this perturbation would look like. The perturbation is probably going to look something like, let's draw a line. So we know actually it's better if I draw this everything on top of each other, then it will be better for your understanding. So our Hart sphere is something that goes up to infinity up here, and then it drops to 0. So that's the Hart sphere, and now we need a reference part. The reference part is going to be the difference of these two. So it's easy to see what the difference would be. Over here, you know, the difference should look just like this line. So it's going to look something like this in this part, right? So if you add red plus blue, you will get black. And over in the part before here, we let it continue this way. Why do we let it continue this way? Because the sum of infinity plus whatever this value is always going to be infinity, right? So let's say this value is -5, and here you have infinity. Infinity minus 5 is still going to be infinity, right? That's the idea. So it doesn't matter how it drops down. You have it's something which drops down at a finite rate and goes towards minus infinity, or even goes to some value. We don't care too much. So this is our U Hart sphere, and this is our perturbation U1. So now we are ready to use the machinery from last time. And what we can say is that, so what do we need for our machinery? Our machinery says that Zn is equal to Zn0. Okay, now I'm going to try to write a bit smaller, not like an elephant. So I think it'll be useful for understanding. E to the power minus beta un perturbation 1, 0, right? This is what the machinery says. So what we need to calculate is this quantity. So let's assume that beta un1 is small. Is this a fair assumption? It is a fair assumption because, okay, so un1 is going to be a sum of these small u1s. So we can think about the u1. So why is it this is a good assumption? In this part over here, it is small for construction, right? Because we have to think whether it is small relative to the reference potential. And here the reference potential has already blown up. So it is mostly small compared to that. So it's not a bad assumption. In this region, it starts to become smaller and smaller and smaller. So as the distance increases, it becomes a better and better approximation. It goes to 0. So maybe there is a region over here where it might be a bad assumption, in this region, but it's not a big region. It's a very small region where it might be a bad assumption. Over here, it's a good assumption. So let's call it A and B. In A, we know that un1 is much smaller than infinity, which is our hard sphere potential. In B, we know that un1 tends to 0 as r tends to infinity. That's the way it's designed, this Leonard-Jones potential. Because so if I extended the line over here, what this potential looks like is that it really goes over to 0. You can see that because typically we assume terms like a by r to the power 12 minus b by r to the power 6, and you can see why this goes to 0. So it's an okay assumption in both regimes. So now we can do something with it since we have this assumption. So if beta un1 is small, then we can say that exp e to the power minus beta un1 calculated in the original ensemble can be approximated as 1 minus beta un1 in the original approximation. We can ignore higher order terms. And then this is exactly 1 minus beta un1 0, which is approximately exp of minus beta un1 0. So essentially what we have shown, in other words, is that e to the power minus beta un1, calculating the average in the reference potential of e to the power minus beta un1 is approximately the same as calculating the average of minus beta un1 and then exponentiating it. This is true only if beta un1 is small. If beta un1 is small. In general, this is sinful to do that. You cannot just get the exponential out of the average. You have to put the exponential inside to do that. For those of you who are mathematically inclined, there is an excellent mathematical relation related to these things, which is called Jensen's inequality, which talks about doing things such as function of expectation value of something. How does it relate to expectation value of that function, depending on whether the function is convex or concave? It is connected to these things. We are not going to get into that. But for those of you who are interested, you might get a kick out of reading that and how it applies here. So this is aside, nothing to do with the main part here. So we can assume this, and this will simplify our life. Why will this simplify our lives? Because we have talked about calculating the average of energies in the past. If you go back, do I even have those notes or did I remove it? If you go back to, did we do it here? We did it like 3-4 lectures ago. I will write down the relation. So 3-4 lectures ago, we showed that so recall, we showed that the total energy of a system is 3/2 kT, which is coming from the momentum part, plus half rho dr 4 pi r square g of r u of r. Does this ring a bell? We did something like that around a few lectures ago. These relations are abstract. These are, before taking this class, you have probably not seen relations like this. You have not thought in terms like this. So even when I see it, sometimes I go like, wait, this is a bit strange. But then when you think about it, it's not complicated. And one of the most important ways to understand this relation is to remember that G rho of R is conditional probability. If you remember that, these things suddenly make a lot of sense. So with this in mind, what was this? This was the kinetic energy. And this over here was the potential energy U. So now we can talk about this is exactly the difference that we are talking about. So we can say that UN10, and why do we need to use this? Because now we need to make the jump. We are talking about an n by the total potential. We are not talking just about the pair potential. So now we suddenly need to make the jump from a system comprised of n interacting bodies. We need to make a jump from a system made up of just small, we need to make a jump from just thinking about pair potentials to a capital UN, which is made up of as a complicated sum over the pair potentials. So that's why we need this relation. But using this, we can write down that UN0 is equal to half rho n. I bring the n, this n to the numerator over here. Dr. Oh, by the way, before I forget, today's material is also not in Chandler. It is Macquarie section 14.2. If you want to go through it and you don't have the book, send me an email. I will take a picture and send to you. I'll scan it and send to you. So we can write it down as half rho n dr 4 pi r square g of r u of r. And we are calling u of r as u1 of r because we are interested in the perturbation. So what does this mean? Wait, did I miss something? Oh yeah. So what is the definition of rho? Rho is n by v. What does that mean? That means n is equal to rho multiplied by v. So this thing becomes half rho, and n is rho v. So rho square v integral u1 of r. Now g of r 4 pi r square dr. So the thing that we are going to do next is subtle but profound. Subtle, sublet, no, subtle but profound. And I want you to take a moment to think about it. So what we did here is we have an average of the energy UN1, which is the perturbation energy, calculated in the reference potential. So perturbation energy in reference potential. So that's why you see the perturbation energy over here. The R itself goes from 0 to infinity. So let's call this equation as equation, let's make this one equation 1 because, sorry. Let's call this one as equation 1 and this one as equation 2. So equation 2 has an integral going from 0 to infinity, and it has the perturbation energy U1, but this equation needs to be calculated in the original unperturbed ensemble. There seems to be nothing in this equation that talks about the unperturbed example. But how could we make sure that this calculation is done over the unperturbed? So this calculation could be done in a system made up of the fully interacting potential, or it could be done over a system where the interactions are only hard sphere. So how do we make sure that this is actually calculated in the heart sphere potential or in the reference potential. What do we need to do here? Any idea?
G of R.
Hmm?
G of R.
So what should we do to G of R?
That needs to be calculated in the
Heart spheres, exactly. So this G of R could be coming from the true potential, or the G of R could be coming from the heart sphere. If G of R was coming from the true potential, then the whole exercise would be completely useless because that G of R is going to be complicated. The G of R for a heart sphere is something that you did in last homework, right? It's kind of trivial. We have done it in class also, G of R. So this is the idea here, that this G of R is for reference potential. And that's why this problem becomes easy to do. Why is that so easy? Because G of R for the heart sphere looks as 0 and then 1. This is sigma. This is GHS of R. This is something you saw in the last homework, also in class. All this is telling you is that you have heart spheres, then the conditional probability of finding another heart sphere at a distance less than R from the first one is 0. You simply cannot find it. And the conditional probability of finding another heart sphere at a distance more than sigma is constant. It doesn't matter how far your heart sphere is because the probability itself is constant. Why do we get that? Because here there is a wall and here there is 0 potential. So that's why the GHF of R looks like this. So we can write this down mathematically. Is 0 if R less than sigma, 1 if R more than sigma. Don't ask me what happens at R equal to sigma. I am not a mathematician, so I'm not going to worry about it. It's discontinuous. So that simplified our life, because what was it that we wrote down over there? We said that UN, capital N, this is the full N body thing, 0 is equal to rho square V. So equation 2 was it equation 2? Yes, it was equation 2. Rho square V by 2, 0 to infinity, U1 of R So by the way, I see that I have a full house today, probably due to my semi-grumpy email. So some of you got worried that it was meant to you. It wasn't meant to anyone. Well, it was meant to a couple of people in particular, and you know who you are. I don't expect you to come to every lecture. That's totally fine if you don't come to every lecture, and you don't even have to tell me that you will be missing it. But you know it when you are pushing it, when you stop submitting homeworks and things like that, assuming that you'll just get a B plus. You know it when you're doing it. So just ask yourself, are you, and if you think you don't know it, then send me an email and tell me, you think I'm making required effort or not? But really, you don't have to worry about coming to every class. The videos are online anyway. And life is complicated right now. In fact, if for whatever reason you cannot make it to a class and just want to watch the videos later, that's also totally fine. Just let me know if that is the case so I understand what's going on. But if you don't show up in class at all and you're not even submitting homeworks, then clearly something is off. So I want to understand what's going on in that case. So now we can write it down using the formula above, which is equation 3. This becomes and we have a 4 pi r square. So let's bring the 4 pi over here. Let's make it 2 pi. So this is 2 pi rho square V. And this integral now has to start only at sigma, because before sigma, G of this is equal to 0 for R less than sigma. So we can start at sigma and go to infinity. Furthermore, beyond sigma, G of R heart sphere is 1. So we can simply replace that by 1. And we are left with U1 of R square dr. So if at this point we had assumed a model for U1 of R, then we could do this integral without any problem and life would be very simple. What we are going to do now is to leave our U1 of R because we want it to be very, very generic. You can apply it to any particular pair interaction you have and call this as, and again, we realize that rho square V is equal to rho V multiplied by V is equal to N sorry, rho square V is equal to rho V multiplied by rho is equal to n rho. So we use that over here. So this is 2 pi n rho sigma to infinity u1 of r square dr. This in turn can be written as minus n rho multiplied by another minus 2 pi, and the minus minus is just for historical reason, whereas the minus minus cancels. You could have left it as a plus, but it's the minus minus happens because of the form that you have seen due to this thing over here. That's why we are getting a minus out, because we want to have something that looks like that. Sigma to infinity dr r square u1 of r, and all of this is a quantity that depends only on the potential, depends only on the perturbation potential, depends on u1, does not depend on rho, does not depend on beta or volume or n, right? So we call this quantity as A. It's not approximate, we call this as the small letter A. So in this, with that, this equation becomes minus A n rho. So what we have shown here is that average of UN1 in the unbiased, in the reference ensemble is minus A n rho. And let's call this as equation number 4, where A is defined through this thing over here inside the bracket. So now we are ready to finally write down our partition function. Again, my favorite formula, which is Zn is equal to Zn0 exp of minus beta un1 calculated in the reference configuration. And we showed that if this thing is small, then this becomes Zn0 exp of minus beta un1 0. This is not true in general. You cannot just move the exponential like that. It's bad idea, but here it works because we have assumed that. And now we know that un0 is equal to a n rho. So this thing is then Zn0 e to the power beta a rho n. Why? Because this is minus beta multiplied by minus a n rho, right? Using equation 4. So we have a simple formula for this. And now we can finally get our equation of state. We can get our pressure. For pressure, don't forget something we did well before this coronavirus thing, which is to get pressure from canonical ensemble. We have the relation P by KT is equal to partial log Zn by partial volume. Now we can do that. It is a product of two things in equation 5. So that is partial log Zn naught by partial volume at what is kept constant, n and t, plus partial of log of this. What is log of e to power something? That thing that you have in the exponent. So this is partial of beta a rho n by partial v, again at constant n and t. So constant n and t. So beta can go out. A did not depend on n or beta, so A can go out. What remains is rho V, rho multiplied by n when we differentiate with respect to volume. So we have to think about it carefully. So write it down again. So what we have is P by KT is equal to partial ln Zn naught, the reference potential, partial volume, at constant nt, plus we are going to get out beta and A. And then it's partial of rho multiplied by N by partial volume at constant N and T. So how do we do that? We have to get rid of rho. We will use rho is equal to N by V. So therefore rho N is equal to N square by V. So therefore P by KT is equal to partial ln Gn naught by partial volume at NT. And beta A we can write as A over KT. And this thing now becomes partial N square by volume by partial V at N constant N comma T. N is constant, so this N square can be taken out. Therefore, P by KT is equal to partial ln Gn naught by partial V at constant NT. N square comes out, that becomes A N square by KT, and you are left with D of 1 over V by dV, that is minus 1 over V square. So this thing is minus 1 over V square. Therefore, P by KT is equal to partial ln Gn naught by partial volume at constant NT minus A by KT, and N square by V square is rho square, right? Since rho is equal to N by V. So this is not quite what you have thought of van der Waals equation of state. We don't talk about partition functions in van der Waals equation of state, but the second term is there. And now you understand why the second term has that interaction form. When you do this van der Waals equation of state in Chem, you don't talk about what is the real basis of A. You just say A accounts for the interaction between things. Now you see exactly what A is in great precision, where A is minus 2 pi sigma to infinity U1 R squared dr. This is a great equation. This is why theorists sometimes feel smug, because you would use A as a fitting parameter in some experiment. But now, doing a bit of theory, you can see what exactly is the molecular nature of that A. How does it depend on the potential?
Excuse me.
Yeah.
Going back to where we found our final form of our partition function, and so we assumed that G of R, when we calculated for U1's expectation value in our reference potential, was the hard sphere G of R. Does that mean our reference always has to be the hard sphere, or?
No, here we took it to be hard sphere. You could take something else.
Okay, so how often is it that our reference potential can be just regarded as the hard sphere potential, or like how often do you encounter things where it has to be more complicated than that?
Oh, it's almost always more complicated than that. And the name of the game in doing this practically is to pick a good reference potential. Typically what people do is to pick a reference potential which is slightly different from the true potential, and then do a ladder. Then take another reference potential which is further slightly different, and you try to kind of approach the hard sphere. That is why these things in practice are actually also called computational alchemy, because you are changing. You want to study the property of some complicated thing with complicated d electrons which are non-spherical and everything, and you can imagine a case where the d electrons, to calculate the property of d electrons, you take as a reference potential s electrons, which are nice and spherical. Of course, the problem would be that the U1 would be very ill-behaved if you do that, the difference between S electron and D electron. But now you can imagine a ladder between that, and how to select this ladder, how to do that. That's why I recommend reading that second paper in context of drug design, where you will see. But here, reference potential seems to work great. That was, I think this was in Zwanzig's 1954 paper. And you can actually read his PhD thesis also. It's online from early 1950s. If you want, I can send you the link, where he talks about all of this in handwritten equations. So it works here, but typically you would never pick a hard sphere. You would do something else which is more relevant. In this case, hard sphere is nice. And you could derive other equation of states by using other other reference potential. I mean, if you have lots of time, go and check it out and see. You might get some new results, which would look cool. Like, if you do that, put me in the acknowledgement of your paper for giving you bad ideas. Okay, good. Yeah, so hard sphere is something we did here. We could do something else, but here we have hard spheres. So almost there. We don't have the full, yeah, please, if you have any question, please don't hesitate. I feel very happy when you ask me questions. This is why I'm not doing asynchronous lecturing to begin with, because I feel like if you cannot attend the class, you can still watch the video later, but some of you can. And in this class, it seems like most of you can. So it keeps for some of the interaction. So now we need to calculate.
My question.
Yeah.
So I guess, I'm having trouble understanding this G of R a little bit.
Mm-hmm.
So for the hard spheres, it was basically just like a step function, right?
Mm-hmm.
So in Chandler, I guess I'm confused. There's this figure, I forget which page it's on, where he draws G of R for a gas, and it's 0, and then it goes up and it peaks, and then it goes back down to 1.
Yeah.
But so even when it's less than the radius of the molecule, it's non-zero.
Mm-hmm.
So is that what? That's not hard sphere then. What is that?
No, because real gases are anything but hard spheres.
Okay, that's using some kind of actual potential.
Typically Leonard-Jones.
Okay.
What is the simplest gas you can think of? A rare gas, right? Argon or something like that. So in fact, I can show you. So if you go and see the first, the first molecular dynamics simulation was done by someone named Anisur Rahman in 1964. This was a physical review paper. As you can see, it's quite important. 3,000 citations is probably much more than that. And in this paper, they calculated G of R by doing simulations for argon, liquid argon, right? It's not gas, it's liquid. And here they got, do they have G? Here, you look at the G of R. This was using molecular dynamics, and you can see all the shapes that they could get. Argon, which is a rare gas, still has a non-trivial behavior. So because hard spheres don't apply to anything, even when you bring two things very close, they are not hard spheres. You do have electrons, you do have all those things existing, and things get crazy. So I can send you a link to this paper, but this was state of the art in 1960s to calculate G of R for liquid argon. This was the first paper on molecular dynamics, by the way. Yeah. Does that answer your question?
Yes, it does.
So it's complicated. Hard spheres are very crude. Okay, so now let's go back to this. And so one thing we can do is to call this as P by KT equal to P naught by KT, because this is the pressure that we expect to happen for the hard spheres, minus A rho square by KT. So we still need to calculate P naught. How do we calculate P naught? Well, P naught is partial log Zn, where did CD come from? Partial log Zn0 by partial volume. So we need to calculate Zn0. How do we calculate Zn0? This is interesting. So if you had an ideal gas, what would be the configurational partition function for an ideal gas existing in a volume V? So let's say we have a volume V and you have n particles existing in that volume. What do you expect this partition function to look like? Any guesses?
V bar n.
Huh?
V bar n.
V what?
V bar n.
V bar meaning?
V power.
V power.
V raised to the.
That's correct, because every particle can exist in volume V and they are independent, so it becomes V to the power n, right? But now you have hard spheres, so it's going to look like V to the power n, but you have to take into account that every particle now has a bit of less volume than the full volume V that it can take. And that thing is going to be given by NB where B is 2 pi sigma cubed by 3. More specifically, it is half multiplied by 4 pi sigma cubed by 3. Why half? Because this is the volume of one sphere. And you have n spheres in the box, so you think of it as n multiplied by this thing, but you have to take double counting into account because you're looking at pairs. So this is our Zn naught, and we have V minus Nb, which is given by this. So now we can calculate our P naught. This half thing is a bit subtle. Go and think about it. You might confuse yourself that it's a bad idea. It doesn't matter. In any case, it's proportional to sigma q. But, yeah. So now we can say, what is P naught? P naught is now going to be partial by partial V of ln Zn naught, ln V minus Nb to the power n. The n can come outside, and we are doing this at constant nt. So n can go really outside, and this becomes n partial by partial V ln of V minus Nb. That's simple. That is simply n by V minus Nb. So let's number this. This equation was, last one was 5. Let's call this equation 6. Let's call this equation 7. So use 7 in 6 to get P by KT is equal to N by V minus NB minus A rho square by KT. And this N by V minus NB can be divided by V both in numerator and denominator. So this becomes rho by 1 minus B rho minus A rho square by KT. And that's it. That's what we wanted to do. So I think this is quite neat. That's why I do it, even though it's not in Chandler's book. We have our van der Waals equation of state. And yeah, so this is the end of the perturbation theory. We are not going to do more than it. This is a wonderful, powerful idea that shows up in a variety of contexts. In my own research, it is quite interesting. So I try to look at machine learning and how machine learning type ideas benefit from statistical physics, and actually people in machine learning are just discovering these ideas. So let's see where it is. Black box variational inference. So yeah, this one, for example. So this conference is the most premier conference in machine learning. It's called Neural Information Processing Systems. And in this conference, they are essentially using, as you can see here, perturbation theory of statistical physics to propose new models, how to train AI and things like that. So these are very recent papers, this is 2017. So these ideas that Zonzig came up with in 1950s have, of course, made a lot of impact in drug design, but now in hardcore machine learning, and these are people like Disney Research and different arenas are starting to use these ideas. And it's not just machine learning, they are useful in a variety of ways. Right now you saw how you can get it to use van der Waals equation of state. And you might not remember all of this derivation, but one thing that I would request you to remember is this formula. Please try to derive it as many times as you need to do it. If for no reason, then because I think you should remember it's my favorite formula. And if you have any interest in this class, or if you think this class was any level of okay, then try to remember this formula. It's a wonderful formula, and it's not hard to derive. It's just multiplying the numerator and denominator by the same thing, and you get this formula. And try to see how you could use it in your research, for example. Okay, so that's it for van der Waals equation of state, and really for perturbation theory, and that's really it for interacting fluids and interacting systems. Now we are going to change gear and try to talk about something which is also very interesting, which is phase transitions and critical phenomena. this material I will be following quite closely, not entirely, but quite closely. And this material is the reason for Chandler's cover. It talks about what we're going to study next. We are going to follow quite closely chapter 5 of Chandler. Oh, by the way, I had a completely unrelated tidbit about this, trivia about this book. So in the first Spider-Man movie, Peter Parker is a student. And if you ever watch that movie, keep an eye out for his bookshelf, and this book is kept on his bookshelf. David Chandler was very proud of that fact till the day he died. That's interesting, I think. I don't know how he got that or why he had this book. Okay, so we will spend a lot of time talking about a model called the Ising model. Ising model is a really, really simple model that talks about how magnets talk to each other. That's how it started in that family, but it's extremely generic. It can be applied to many, many, many things. It has led to at least 2 Nobel Prizes. On Sagar won a Nobel Prize for it. I think someone else also did. It has inspired countless ideas in a variety of ways. There are still lots of open problems in the context of Ising model, which if you could solve, you could still get a Nobel Prize. And I will tell you some of these problems. I will not just tell you there exist problems. I will tell you what these problems are, so you can go and solve them and get a Nobel Prize. So
apparently on the archive, there's a paper called Attacking the COVID-19 with the Ising Model and the Fermi-Dirac Distribution. So it's very relevant.
Yeah, how topical for us. Yeah,
I don't know. This preprint server, bioRxiv, this morning just put out an announcement. They are not going to accept any paper, any preprint related to COVID-19 if it's a purely computational preprint. They said no, because so much crap I myself have reviewed multiple papers on computation, purely computation to design COVID-19 inhibitors, and some are good, some are not so good. Anyway, the Ising model is very simple. The inspiration comes from having a bunch of magnets. So let's say you have magnets in a one-dimensional world. Oh, my screen share has stopped. I can see. So let's stop it. Stop share. And let's do it again. Okay, good. So let's imagine you have spins in a 1D world. Okay, let's not go into 2D right now. Let's say it's just a 1D world. You have magnets where the magnets can point north-south, or they can point south-north, right? Well, what do I mean? I'm confusing things. So the magnets can point up, or the magnets can point down. So some are pointing up, maybe some are pointing down, like this. I don't even want to use color here, which is just going to confuse things. I'm just going to draw everything in the same color. So you have some magnets up, some magnets down. Now let's say you bring a massive magnet in parallel, mega magnet, which is aligned like this. This mega magnet faces this way. It's pointing up. Its north pole is pointing up. What would this mega magnet do to all these little magnets? They will all also like to align with the mega magnet, right? They will all like to be like the cool guy and look like this, right? And if suddenly the mega magnet started acting this way, all these little magnets would try to act this way. That's one thing in the presence of an external magnet. Let's call the strength of this external magnet is H, the external magnetic field. So that's not the only thing that is dictating how these magnets will align. If you had no magnet, then you would imagine that if the first magnet is up and the second magnet is up and the third magnet is up, probably the fourth one will depend on how these magnets are behaving, right? The fourth magnet also might try to act up or something, right? They try to all align in the same direction. So in order to think of how do magnets align in the presence of some external magnetic field and also due to self-interaction, we can think about the energy of the system, E. This energy is also called the Hamiltonian. There is no kinetic energy here. So that's one thing that's going to change from this part. We are not going to really think about kinetic energy. We will just think about interaction energies. So there is no kinetic energy. So the Hamiltonian is simply the interaction energy. Will be given by, and let's say we call all these magnets or spins. So we can think of these as spins, S1, S2, S3, S4. And let's say this one is a spin plus, and this one is a spin minus, plus, minus. And this is right now a plus. So if this big one is a plus, maybe all of them would try to align in that direction or maybe opposite direction, depends on the physics. So let's write down the interaction potential that shows us exactly how this will all behave. So the first term will come from the interaction between these spins and the external potential. And that will be given by I is equal to 1 to n. Let's say we have n spins. External magnetic field multiplied by the moment of every magnetic and the spin, whether it's up or down. So any physical system in absence of entropy just wants to lower down its energy, right? So you can see that if H is positive, so if H is in this way and it's positive, then the way to lower energy that it would be that, so if H is 0, simply on this basis, you would like all SI also to be more than 0. They would like to align in the same direction. That's what you see over here. Why? Because then this energy would become negative. But if H was less than 0, then SI would also like to be less than 0 because that would again lead to negative energy. This is if there is only external magnetic field. But the spins also do talk to each other. The magnets are talking to each other too. And that's why you have a second term, which is so this is our external energy. And we have a second term, which is what we will be worrying more about, is how do two magnets talk to each other? And that will be a product of the moments SI and SJ for I not equal to J. And this is where everything gets a lot of fun. If J is positive, then the way to reduce energy would be that SI and SJ have the same sign. And that is what we call ferromagnetic coupling. So if H is equal to 0, let's not worry about external magnetic field, and J is positive, then SI, SJ for all IJ would like same sign, right? If J is negative, then the way to reduce energy would be SI and FJ opposite signs, and you would have antiferromagnetic coupling. So this is ferromagnetic, and this is antiferromagnetic. And you can have a lot of fun by seeing how these spins align in their minimum energy configuration. As you start increasing temperature, there will be more and more disorder. So we are going to look at this. Oh yes, I just remembered the second Nobel Prize, which was related to Ising model. So the first one was for Onsager. And the Ising model was given to Onsager as a little problem, as his PhD problem. He solved it and he won the Nobel Prize for it. Later, the same problem was attacked in higher dimensions by Ken Wilson, who then discovered something called renormalization group theory. We'll be talking very briefly about it. It's one of the fundamental ideas in statistical mechanics. Along with Ken Wilson, Michael Fisher worked on it for many, many years. He nearly won the Nobel Prize. He won many other Nobel Prizes for it. Michael Fisher is a professor emeritus in our own chemistry department. 15 years ago, he used to teach Chem 687. That would have been a good time to learn statistical mechanics from Michael Fisher. Now you're stuck with me. You will laugh. Okay, good. So I don't know, that's good or bad.
I had a question.
Yeah, please.
Could you define those terms a little bit more for us? So what is mu and what is J?
So mu is, for all practical purposes, 1. It is just a unit for how strong is every magnet. Okay, it's just a unit for the magnetic moment. You know, when you measure anything, you have a unit for it. It's just is setting the units for that. H is the strength. Yeah, sorry, I didn't write it down. H is the external field. And J is the interaction between spins. Okay? So J is the interaction between spins, how spins talk to each other. And I will give you a way for how to develop more intuition for this. So most of the time, we will work with systems where H is equal to 0. We are not going to worry about the external magnetic field. We will simply think of systems where the energy is given by minus J, I not equal to J, Si multiplied by Sj. Okay? So you can see what this means. If J is equal to 1, for example, so this means E is equal to minus Si Fj. And the way to minimize the energy would be that all spins have the same sign. Either all of them point up or all of them point down, right? And if J was equal to minus 1, then the energy would be sum Si dot Fj. And then the minimum energy arrangement would look something like this. Now it gets very complicated because we are not just talking about nearest neighbors I of j, we are talking about all ij's. This spin is talking to this spin. That's what makes it complicated. So I have friends who work at Facebook research in New York, and they use Ising models heavily to model how people on social media talk to each other. This is you, and this is your network of friends. Facebook is not a 1D world. It's a high dimensional world, right? So how do opinions change there? So up could be, for example, Republican leaning, and down could be Democratic leaning. So if this one is Republican leaning, does it influence this other one to become Republican leaning or Democratic leaning? Maybe you hate your neighbor. In that case, you want to be as different from your neighbor as possible. You're like, oh, he has a Bernie 2020 sign. I want to do something opposite to it. So that's antiferromagnetic coupling, and you things like that. And as we go through this, you will see how this is applicable to all of this, or it can be used to model all of this. The point I want to mention right now is, in the absence of spins, you can talk about, so this is individual spin, and in the absence of spins, you can talk about the net magnetization of the system, M, with the average value of this M, which we will write as modulus that way, or in bracket notation, will be given by going to every spin from 1 to n, calculating its magnetic moment. That's the unit, whether it's a little magnet or a big magnet, it's kept same everywhere. So in principle, we don't even have to worry about mu, but we kind of keep it because it's nice. And it plays a role later, actually, multiplied by the spin. So if you had a configuration like this, then the magnetic moment would be mu minus mu plus mu minus mu dot dot dot. So this is plus mu, this is minus mu, this is plus mu, this is minus mu, and the net would be 0. If you have all spins in one direction, then the magnetic moment would be n mu, right? So the most important question that has led to Nobel Prizes in this field, and that still has scope for more Nobel Prizes, is how does the magnetization depend on temperature? What would you expect to happen? And again, this is all in the absence of magnetic fields, okay? So at very high temperatures, there is no reason to expect that spins would be aligned, right? At very high, and I think of it as a nice analogy for all of this is that game of Jenga, right? At high temperature, why should the Jenga be very well behaved? Not Jenga, what is that thing where, there are those YouTube videos about it where, and especially this, when people get bored, they make these videos where you have one thing standing over here and something else over here, and then you push this one and it moves this one and it moves this one. And the effect just goes percolating, right? So at high temperature, none of that is going to stand. They are all going to be disordered. So at high temperature, it is quite clear that the net magnetic moment should be 0. It should go to 0 at a very high temperature. And at 0 temperature, it is clear that things should be in a ground state. Ground state means they should occupy the minimum energy configuration. So in general, this magnetization should go to 0 at some temperature, which is called the critical temperature. So at a very low temperature, we expect things to be ordered or magnetization not equal to 0. At a very high temperature, we expect things to be disordered or the magnetization equal to 0. And this temperature is the temperature at which we say that a phase transition has occurred. Now, all of you are coming from, I mean, this class has students from 6 different departments, which is, I think, a record for 687. But irrespective of whether you are in chemical physics, biophysics, chemistry, whatever, you will be dealing with phase transitions at one point or the other. And typically phase transition, this is the best example of a phase transition. When a certain property, magnetization, more generally, this is called as an order parameter. An order parameter changes from non-zero to 0 is a phase transition. So, and so an example of a phase transition could be magnets are the most typical example. You have magnets all oriented in one direction, magnets all disordered, or you could have a phase transition where metal becomes an insulator, right? This is very popular in quantum mechanics and in solid state physics. You have these Mott insulators where a semiconductor becomes an insulator. Students such as Shokang over here is working on battery materials. The conductivity goes down to 0. These are all examples of phase transition. So the most, did anyone have a question?
Yeah, just as an aside, like when you have Bose-Einstein condensation, if you have like some kind of a interacting Bose gas, it has the same functional form.
Yeah.
As this right here. You see the same behavior.
Yeah, exactly. And phase, so being able to control this phase transition is of great interest, because then you could design materials for storing memory by controlling whether you are in one phase or another phase. You can do lots and lots of wonderful things. What we are going to prove next is a relation of enormous fundamental importance. There are no phase transitions in one dimension. That's what we are going to show next. In other words, the critical temperature for the average magnetization to go to 0 in one dimension is 0. As soon as you introduce any thermal fluctuation in the system, the magnetization will drop to 0. As you increase the dimensionality, this curve starts to look like this. In 2D, the critical temperature will be typically higher. In 3D, the critical temperature will be even higher. What Onsager did was to calculate the critical temperature for a 2D Ising model. So over here, the interaction potential that I defined was for spins that are aligned in 1D, right? But you could also imagine a model where the spins are in 2D. And instead of numbering sites just here, 1, 2, 3, 4, why stop here? You could keep going, 5, 6, 7, 8, 9, 10. You could define the full thing in 2D, right? And what Onsager did was to derive the critical temperature in 2D Ising model. This was my first undergrad project to do this in a code. So I still remember the answer. It is something like 2 by ln of 1 plus root 2 in units of, okay, I'm missing the unit, but it's proportional to something like this. He derived this exactly. For this, he won the Nobel Prize. In 3D, there is still no analytical derivation for the critical temperature in Ising model. If you can do it, you will win a Nobel Prize. I mean, I'm ready to bet $1 million to you that if you derive analytically the Ising model critical temperature in 3D, you will win a Nobel Prize. If you don't, I will give you $1 million, because I'm sure we'll figure out some other way to make money out of it. You will win that Nobel Prize. Maybe I should not say that. It's too risky. Okay, I will leave it at $10,000. Million is too much. Things can happen. So what people have tried to do for this is to think about 3 minus epsilon dimensions or 2 plus epsilon dimensions, which don't even ask me what does it mean to think about 2 plus epsilon dimensions. These are mathematical ideas using differential geometry, this, that, blah, 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 whatever. And you can go and see papers on this. There are lots and lots of papers. So we are already seeing some very interesting things. So you cannot have basically an ordered material. So if you have, let's say you have some polymer, you have a conducting polymer, right? And in order for this polymer to conduct, different parts of the polymer must be metallic. They cannot be insulated, things or something like that. And if you force this polymer to be a 1D polymer, you will never be able to have a fully conducting polymer. As soon as you have any finite temperature, it will become disordered. Somewhere you will have a break. You have to go to 2D to get a critical temperature. And as you start to increase the dimension, this critical temperature becomes higher. So it is quite generic that the critical dimension versus critical temperature versus dimension behaves something like this. I'm not saying whether this is linear or non-linear. I don't know. All I'm saying, but I'm not also saying whether this is convex or concave. I don't know or whether this is even smooth or rough. All I'm saying is that it goes up. Next class, we are going to use a very simple argument to see as to why is it that in one dimension there is no critical temperature and that in higher dimensions there is a critical temperature. And before we do that, I want you to go and play with a certain app that I posted on the website. You see my website, right? The class website. So if you go here, I have posted an app that John Weeks made, which is super cute, which allows you to play with 2D Ising model. So this is the cover of Chandler's book. So what you have over here is blue corresponds to spin up and yellow corresponds to spin down, okay? So you set it up. You can also set up nanotubes here and all kind of funky things. But let me take 10 to second. So you set it up and you give it a temperature. So here I have given it 2.27. That is the critical temperature. That is beyond which things go funky. That is the 2 by log of 1 plus root 2 thing that I wrote is actually close to 2.27. So now you can, and it has periodic boundaries. So the spins at the end over here talk to the spins on the other side. Okay. So now you can start the simulation. And what you see is that it kind of stays disordered. The overall magnetization of this thing is still 0. There are roughly as many blues as many yellows as you have. So what you're doing here is to execute something called Metropolis algorithm. If you want, I can tell you more on it. It's too much for this class currently. But you are allowing every spin to change from plus to minus. And at a high enough temperature, it kind of stays disordered. Now we can change the temperature even higher. Let's try it at temperature 25. And we pause and we start at temperature 25. Oh, now you're not seeing what I had over here. Let me stop share and start again. Share screen. Okay, so this is at temperature 25. You see it's really, really disordered, right? You can see why the domains are even smaller. Now let's go to a very small temperature. I told you the critical temperature is 2.27. Let's go to a temperature which is 0.01. And now see what happened. Suddenly you have big domains. And if you run it long enough, everything will become either yellow or become red or blue. And the system is degenerate with choice of yellow or blue. Why? Because in absence of an external magnetic field, it doesn't matter whether all your magnets are pointing up or all your magnets are pointing down. It simply doesn't matter. So if we decrease the temperature even further, let's make it 0.0001, pause, start. No, first I have to randomize. Where is the randomize? Randomize. And now see what's happening. The domains are becoming even bigger. And there are lots of funny things happen here. If you had two domains, the smaller ones will tend to get even smaller and the bigger ones will tend to get even bigger. In material science, that is called Ostwald ripening. In society, that is called as rich getting richer and poor getting poorer. And you can see all these things over here. So you get this critical, and you see it's all yellow now. It could also become all blue and in the absence of an external magnetic field. And you can see on the right that the energy is still decreasing. Average energy you see over here is minus 1.9. So you can play with all this. It's a lot of fun. You can also do these things called, he also has some in nanotube setting, and there are lots of things you can play with. But you got a critical temperature here. In 1D, it would always be disordered. You would never get an ordered material. And that's what we are going to show using something called a Pearl's droplet argument in next class. Then we will go to mean field theory. And mean field theory gets it wrong in higher dimensions. And then we will introduce renormalization group ideas. And that will pretty much be the end of this semester. Okay, so I have office hours today. Last time one student came, which was great. I was getting lonely. And today I will again be there 3 to 3:30 if you want to come and talk about any of this. Otherwise, see you next Tuesday. Thanks.